Hello, everyone. So let me just remind you, we have exam on the Thursday, next week. I just want to remind you that we are going to cover chapter 01 and part of chapter 2. So from chapter 0, we have homogeneous and non-homogeneous equations. From chapter 1, we talked about Fourier series. We talked a lot about that. We cover a lot of sections, 1.1, 1.2, 1.3, 4, 5, 9, 10, and 11. From chapter 2 up to now, I think we talked about 2.1, 2.2, and 2.3. And today, I think I should start 2.4. 2.5 and 2.6, they're just examples. There's nothing new there. So you can read them for the exam. The reason I did not mention 2.5 and 2.6 is that they're just examples. They're not new chapters, right? They're just some examples which could appear in the homework or in the exercise. And then after talking about 2.4, we will start 2.7. Hopefully we can finish that this week, so you have enough time to review for the midterm. However, because I do not have enough time, the semester is very compact. Next week I should continue, right? We can't review for the homework. So there, a few of you asked, so I would just say it here one more time. On Monday, I will going to have office hour from 8 a.m. to 9 a.m. I have office hour. And then I have MLC hours from 11 a.m. to 1 p.m. Okay. So if there is any question, you can ask me there. Also, in each meeting on next week, we have 2 meetings before the exam. We can have 15 minutes time for Q&A. If you have any question, next week on Monday and on Wednesday, the last 15 minutes of every meeting, we can discuss if you have any question or there's something you're confused about, we can talk about that. Okay. So, okay, that's enough. Let's, if there isn't any question, let's start the equations we were talking about. Is there any question here about these things? Okay. So, okay, I think we talked about the section 2.4. Oh, what will be the format of the exam? Well, I mean, it would be quite standard. I would just give you a few equations, or I have not written the exam yet, but it would be just a few equations and you should just solve them. It's not going to be anything surprising to you, just like what we did in the class and almost what you saw in the homework. Some questions might ask you to kind of, I'm not going to ask you for any proof of any theorem, but sometimes I might want you to argue for something. So just like, for example, show that this equation has no non-trivial solution or something of that sort. So basically everything reduces to solving some equation. Or, well, of course, one chapter is Fourier series, so you should be able to write down Fourier series of a function. Yeah, just like that, very, very standard. So hopefully if you just review like the videos and the lecture note or take a look at the book, you can easily handle the exam. Okay, let's start. So on Wednesday, we talked about this equation. The sort of the equation we had was like this. The second derivative of u with respect to x was equal to 1 over k derivative of u with respect to t, right? That's what we had. So that was the equation. I still want to study the same equation. Now, the thing which is going to change is the boundary value condition. So the boundary value conditions we had yesterday, it was the constant boundary value condition. So u of 0 and t was equal to a constant t naught. U of a and t was equal to another constant, right? T1. And we had an initial condition, which was telling us that u of x for any point x, well, x is between 0 and a, right? This is a rod, and then here x is equal to 0, here x is equal to a. U of x at the time 0 is given. It's some f of x. This was the equation which we studied, right? For any positive time. Now, we found the solution to this equation, and the way we solved this one was first solving the steady state equation. We defined a function v of x. We defined this function to be limit of u of x and t when t goes to infinity, assuming it would converge to something. And then we wrote down the equation for v, and we solved that equation, and we got the steady state solution. The second step was writing u as the sum of this v plus another function, w of x and t. And then we wrote the equations for w. So the equation actually doesn't change. The equation is the same thing. We get the same equation. The good thing here is that boundary value conditions, they became a lot easier to handle. So w of 0 and t is equal to w of a and t equals 0, which that was good. The initial condition simply changes. The initial condition was equal to, well, f of x minus vx, just another one. And then we solved this one. We solved this one using the product method. Okay, that's what we did. Now we want to kind of tackle very similar problem with just a different boundary value condition. Okay, that's what we are going to do. Is there any question about this method, the things we did on Wednesday? Everything is clear here? Okay, so let's continue. So now we want to solve a similar problem, and the equation is the same. So this is the section 2.5. If you're following the book, the equation is the same. The second derivative of u with respect to x is equal to derivative of u with respect to t for any x between, again, for any x between 0 and a. This is the x-axis, and for any positive t or non-negative t. Now we have the boundary value conditions. So at one end, at x equal to 0, we take the same boundary value condition. We say the value of u at one of the ends is fixed. It's t naught. At the other end, we take what we call the second kind boundary value condition, or Van Neumann boundary value condition. So the other condition, it does not fix the value of u here. Actually, it fixes the derivative of u at that point. It tells us that if at this point, if we go, for example, to left, for example, in this case, the value of u infinitesimally does not change, which means its derivative at the point a is going to be 0. And then we would have an initial condition which tells us that u of x at the time 0 is equal to a given function f of x. Okay, so similar equation, slightly different boundary value condition. Okay. So again, the way to solve this problem is to look at the steady state solution. So assuming when a good amount of time passes, the function u becomes kind of constant. It doesn't change by time. So assuming that the change in u with respect to time after a good amount of time, so let's say when t is large enough, is 0, it means that the function u at each point x would converge to some constant number. So limit, so suppose that, and then it means limit of u of x and t when t goes to infinity would converge to something. I would call that number to be v of x. So it gives us this steady state function, right? So first we should solve this equation for this steady state function. How can we do that? We'll look at our equation here. We take limit with respect to t, and we send t to infinity. Right. Now, well, we know u will converge to v. So the left-hand side becomes the second derivative of v with respect to x. Right-hand side, 1 over k is constant. Partial u partial t, well, our assumption says that is going to 0. So the right-hand side is just 0. Right. Now we can solve this one to find v. So the second derivative of v with respect to x is 0. Apply antiderivative to both sides with respect to x. The derivative of v with respect to x should be a constant. Therefore, v itself should be equal to a constant times x plus another constant. So applying antiderivative with respect to x 2 times, we get v is equal to cx plus d for 2 constants, c and d. Is there any question here? Is everything clear on this page? Okay. So now we know what v of x is. So let's call that v of x. Now, remember, we also have these boundary value conditions, right? So one boundary value condition was u of 0 and t is equal to t naught. The other one tells us that the derivative of u with respect to x at the point a at any time t is equal to 0. Now, taking limit, we can take limits from both of these equations. We can take limits from u0 and t, send t to infinity. And the right-hand side would be the limit of some constant, which, well, it would stay the same constant. This thing is going to be v of 0. So v of 0 is equal to t naught. That's one equation. What about the other one? Let's take limit of this one and send t to infinity. So limit of partial u partial x at a and t when t goes to infinity is equal to 0. Well, u would converge to v when t goes to infinity, so it becomes partial v partial x at the point a is equal 0. So we have 2 equations. So we have 2 conditions for the boundary value properties for v, for the steady state solution. One of them is v of 0 is equal to t naught. The other one is partial v partial x at a is equal to 0. Now, actually, we computed v in the previous page. We saw v of x is equal to cx plus d, right? Well, That implies v of 0 is equal to the constant d. Just plug in 0 into x. On the other hand, this condition here tells us v of 0 should be equal to t naught. So d is equal to t naught. That's one piece of information. On the other hand, the other condition is telling us something about the derivative of v with respect to x. We can take derivative of v with respect to x. Derivative of v with respect to x is equal to c, right? But look at this condition here. This condition says derivative of v with respect to x at the point a should be equal to 0. However, here we understand derivative of v with respect to x is a constant. So this constant should be equal to 0. So c is equal to 0. That completely identifies what v is. V of x is equal to cx, which is 0, so 0 times x, plus d, which is t naught. So v of x is this constant function t naught. This is a constant function. It doesn't changes anywhere along this rod. It's so along this bar, everywhere from 0 to a, v is equal to the constant t naught. So this is our steady state solution. Is there any question here from this page? Is everything clear how we compute this steady state condition? Okay, great. Okay, so now that was our first step, to find the steady state solution. What is the second step? The second step is saying writing u of x and t as v of x plus another function w of x and t. And then writing down the equations for w, right? We did that earlier. We do again here for this problem, just as a review. So our equation was the second derivative of u with respect to x is equal to 1 over k derivative of u with respect to t, right? Now let's compute these variables here and see what are they with respect to w, right? So in order to do that, I would take derivative with respect to x from this equation star we have here. So derivative of u with respect to x is equal to derivative of v with respect to x plus derivative of w with respect to x, right? Let's take the second derivative. The second derivative of u with respect to x would be the second derivative of v with respect to x plus second derivative of w with respect to x. Okay, we know the value of one of these terms. Do you recall which term it is? Between these three terms here, we actually know the value of one of them. Yes, that is correct. So if we go to the previous page, remember what is the equation that v should satisfy? This is here. The second derivative of v with respect to x is 0. That's great, because here we have the second derivative of v with respect to x, and that is equal to 0. Okay, so let's look at the remaining part of the equation. It tells us the second derivative of u with respect to x is equal to second derivative of w with respect to x. Great. Now there is another part here, derivative of u with respect to t. So we take derivative of this equation star. Now we take derivative with respect to t. So derivative of u with respect to t is equal to derivative of v with respect to t plus derivative of w with respect to t. However, v is not even a function of t. It's just a function of x. So when we are taking derivative with respect to t, v is like a constant. It does not depend on t, and therefore its derivative with respect to t is 0. So the remaining part of the equation says partial u partial t is equal to partial w partial t. If we plug these things into this equation we have here, if we plug in this part, we see the second derivative of u with respect to x is equal to the second derivative of w with respect to x equals to a constant times derivative of u with respect to t. Well, that also from here we know it's equal to derivative of w with respect to t. So we get a very similar, well, the same equation for w. So the first part is that now we know the second derivative of w with respect to x is equal to 1 over k derivative of w with respect to t. That's what we knew from before too. Now, we should find what are the boundary conditions for w, and this is the interesting part. So one boundary condition for u was this one. U of 0 and t was equal to a constant t naught. That was part of the data. The other part of the data was the derivative of u with respect to t at the other boundary point a at any time t is equal to 0. Okay, now I want to see what are the boundary conditions for w. I should just take limit of these boundary conditions and send t to infinity. So if I do that for equation for the condition number 1, I would see limit of u of 0 and t when t goes to infinity is equal to the constant t naught. Now this limit is equal to v at 0. This is equal to v of 0, right? On the other hand, so remember v of 0 was equal to t naught. On the other hand, u is equal to v at 0 plus w of 0 and t, right? U is equal to their sum, and this is equal to t naught. Now, if v of t naught is equal to t naught, it means that t naught plus w at 0 and t is equal to t naught. We cancel these two. We see that w of 0 and t is equal to 0. We had computed this before. It was just, again, a review. Now, the second part is new. Let's see what the second equation would be for. What would it be for w? Okay. Is there any question here from this computation? Is everything clear? Okay. Now, looking at the second equation, partial u partial t at the point a and t equals 0. If we take limit of this thing and send t to infinity, we would see that limit of partial u partial t send t to infinity at a and t, it should be equal to 0, right? Sorry, partial, there's a typo here. I hope I'm not, did I make this? It's derivative with respect to x, hopefully. Let's see if I made the same mistake. Yeah, sorry guys, this thing, I have the typo here too. It's derivative of u with respect to x. Okay, great. So we can take t to infinity, and we saw derivative of v with respect to x at the point a is equal to 0. So that was one condition. On the other hand, u is equal to v plus w, and therefore derivative of u with respect to x is equal to derivative of v with respect to x plus derivative of w with respect to x. Now at the point a, this condition says derivative of u with respect to x is 0, right? So if x is equal to a, this thing here is 0. What about derivative of v with respect to x at the point a? Well, this other condition tells us that also would be 0, plus the last term is derivative of w with respect to x at the point a. and therefore this is the other boundary condition. Derivative of w with respect to x at the point A is equal to 0. This is our second boundary value condition. So now we have two boundary value conditions for w. Okay, so writing them next to each other, our equation for w is this. And our boundary value conditions are these. And if you remember, the initial condition was also w of x, and the time 0 is equal to f of x minus v of x. But v of x here, remember, is just constant t naught. So this is the equation that we should solve now. This is the equation with the boundary value condition and the initial condition. This is the equation we want to solve for x between 0 and a and t positive or non-negative. Now, usually here, when these boundary value conditions are 0, we call this problem homogeneous. So homogeneous. So it's a slightly different with the homogeneous problem we had before, but actually they are similar in the sense that we want to translate this problem into some ODEs when these boundary value conditions are homogeneous, when both of them are equal to 0 rather than t naught or t1 or other things. When we break this PDE into ordinary differential equations, those equations would be homogeneous in the sense that we had in chapter 0. Remember, when we had an ODE, depending if the ODE, the terms having y, if it was equal to a constant non-zero term or a 0 term, we were naming them to be homogeneous or non-homogeneous. That's what is happening here. That's the whole idea behind writing the equation and boundary value conditions for w. Okay, so we are going to try to solve this thing the same way we did before. We try to solve this using the product method. This is what we did for the other function yesterday, I think. Okay, so product method means suppose this function, which we are looking for, this is our unknown, is multiplication of two functions. One is a function of x, one is a function of t. We did this one on Wednesday for another problem, and it worked there perfectly. We could solve the equation there. Let's see for this new boundary value condition if this technique also works here or not. Okay, so again, I would write our condition on every page because this is what we are trying to solve. Okay, because the condition is this, the equation is similar to the equation we saw before. The equation for f1 and f2, of course, are also similar, but I would write them again. So derivative of w with respect to x would be derivative with respect to x of f1 of x, f2 of t. f2 of t it does not depend on x, so it comes out of derivative. So we have derivative of f1 with respect to x. If we take the second derivative of w, because that's what we care about in this equation we have, we would see this, it would be equal to f2t, the second derivative of f1 with respect to x. Great. Also, the derivative of w with respect to t is equal to f1x, derivative of f2 with respect to t at the point t. Okay, so the equation tells us that this thing here, which is equal to f2t, the second derivative of f1 with respect to x at the point x should be equal to 1 over k f1 t f1x, the derivative of f2 with respect to t. Right, that would be our equation. Again, what we do here, just like always, anytime that we can, we would separate the variables. That's a very good thing to do if we can. So we can take, for example, we can take everything which has t in it to one side. For example, I can take this term to the right-hand side, and I can take this term to the left-hand side. So I would divide everything by f1 times f2. So here we would get the second derivative of f1 with respect to x over f1 is equal to derivative of f2 with respect to t over f2 or kf2. Where the left-hand side, everything is a function of x, and on the right-hand side, everything is a function of t. They are equal. Now remember that, as I mentioned the other time, because one of them is a function of x and the other one is a function of t, they can be equal only if these two are, both of them are equal to constants. They don't have any x or t in these forms, right? So we had these before. This is what we did before. Now let's look at the boundary value conditions. So the first boundary value condition was w at 0 at any time t is equal to 0. It means, well, w was f1 times f2. f1 of 0 times f2 of t should be 0. So there are two cases. Either f1 of 0 is 0 or f2 of t is 0. But the second one means for all t, for every t. And if that's true, well, then w would be 0 because w is f1 of x times f2 of t. So it means w is equal to 0. That's not what we're looking for. So the second case is not valid, is not acceptable. So the first case should be true. f1 of 0 is equal to 0. That's the first boundary value condition. Let's show that with star. Okay. The second boundary value condition was derivative of w with respect to x at the point a and t is equal to 0. Now, derivative of w with respect to x is equal to derivative of f1 with respect to x at the point a times f2 of t is equal to 0. Again, multiplication of two terms is equal to 0. It means either the first one is 0 or the second one is 0. Well, again, if the second one is 0, w would be 0. We don't want that. Therefore, the first case is the acceptable one. Derivative of f1 with respect to x at the point a should be 0. Let's show that with star, star. This would be our second boundary value condition. We have two equations, two boundary value conditions. Okay. So what are these two equations? These two equations are these two. One of them says this fraction here should be equal to the constant. The other one says this fraction here should be equal to the constant. We had one boundary value condition for this one, one boundary value condition for the other one. Okay. So here we have a constant, let's call that constant c. Always what we should do here is to understand if this constant is positive or 0 or negative. Okay. So And usually we should use our boundary value conditions as we did before for different boundary value conditions. So we would have 3 different cases. So this is what you should do every time. Either C is positive, or C is 0, or C is negative. Is there any question up to this point? Is everything clear? Everyone's following? Okay. Okay, let's start with the first case. So let's see. The second derivative of f1 with respect to x over f1 equals derivative of f2 with respect to t over f2 is equal to c, where this c is positive. So it gives us 2 equations. One is the second derivative of f1 with respect to x minus c f1 is equal to 0. That's one condition. The other one, derivative of f2 with respect to t minus cf2 is equal to 0. Okay. We also had some boundary value conditions. What was the boundary value condition for the first equation? That was, okay, where was it? Let's see. What was our boundary value condition? I think we had them. No, not here. Here. f1 of 0 should be 0. That's the boundary value condition here. f1 of 0 is equal to 0. This is the boundary value condition. What was the boundary value condition for f2? Did we have any boundary value condition for f2? Here we have another condition. Well, we can't have any boundary value condition for f2. This other one is also a boundary value condition for f1. Derivative of f1 with respect to x is equal to a. So there is a second one. Derivative of f1 with respect to x at a is also equal to 0. So we have these 2 boundary value conditions. For f2, it's a function of t. We have the initial condition. So what is the initial condition? So w at any point x and 0 was equal to fx minus vx. W is equal at x and 0 would be equal to f1x times f20 is equal to fx minus vx. It's not very helpful because here we have f1 now. It would be a little difficult at this point. Let's not follow that. Let's focus on the first equation. So let's focus on this equation with these boundary value conditions. This is the one we are going to study. Okay. So this is a second order linear homogeneous equation. What we should do is to look at the characteristic polynomial. So the characteristic polynomial or characteristic equation would be m squared minus c is equal to 0, where c is positive. So m would be plus minus the square root of c. So in this case, the solution is equal to a constant. Let's show that with c1, e to the square root of cx plus another constant, e to the minus the square root of cx. And then let's check. This thing should satisfy the boundary value condition. The first one said f1 of 0 is equal to 0. So here, if we plug in, if we let x to be 0, f1 of x would be equal to c1 times e to the 0, which is 1, plus c2 e to the 0, which is 1, should be 0. So C2 is minus C1. And then if we take the second condition was the derivative of F1 with respect to x at a is equal to 0. Let's take derivative of f. Derivative of f with respect to x is equal to C1 square root of C e to the square root of Cx minus C2 square root of C e to the minus square root of Cx. Plug in x by a, substitute x by a. You see C1 square root of C e to the square root of Ca minus C2 square root of C e to the minus square root of Ca is equal to 0. Now we know C2 is minus C1, so here, rather than minus C2, we can write down plus C1, right? Now, we can assume C1 is non-zero, because if C1 is 0, C2 is also 0. Everything would be 0. That's not what we are looking for, the constant 0 solution. And assuming C2 is non-zero, we can divide everything by, assuming C1 is non-zero, we can divide everything by C1. Also, we assumed C is positive, so C is not 0. We can divide everything by C, by square root of C. So if we divide everything by C1 and divide everything by square root of C by their multiplication, we get e to the square root of Ca. If I take the rest to the other side, is equal to e to the minus the square root of Ca. Is there any question here? Okay. Let's come back here. Okay, let's see if C can be 0 or not. So if C is 0, the second derivative of f1 with respect to x would be 0. That would be one of the equations. The other one would be derivative of f2 with respect to t is 0. Right? So the first one says derivative of f1 with respect to x is a constant, call that C1. Therefore, f1 is equal to C1x plus C2. Now let's try the boundary value conditions again. f1 of 0 should be equal to 0. That was one of boundary value conditions. The other one was this one. So f1 of 0 is equal to C1 times 0, which is 0 plus C2. That should be 0. So C2 is 0 here, no C2. Derivative of f with respect to x is C1. This should be 0. It means C1 should be 0. Well, therefore, f1 is 0. If f1 is 0, w was f1 times f2, w would be 0. That's not what we are looking for. We are not looking for a trivial solution. So that's not the case. That's not the case we are interested in. So C can't be 0 either, just like, again, the previous problem we solved. So let's start with the third case, C being negative. Well, if C is negative, minus C would be positive. So minus C is equal to some number squared, call that lambda. Okay, so C would be minus lambda squared. Okay, so we had two equations. One was the second derivative of f1 with respect to x. This should be equal to minus lambda squared times f1 of x. We can take the right-hand side to the left-hand side. We see the second derivative of f1 with respect to x plus lambda squared f1 of x is equal to 0. That's one condition. Let's say that's one equation. Let's call that equation number 1. The other equation was derivative of 2 with respect to t over f2 is equal to this constant, and therefore this is equal to this constant, which now we call it minus lambda squared times f2 of t. That shows the derivative of f2 with respect to t plus lambda squared f2 of t is equal to 0. So we have these two equations. These are the two equations we should solve. Okay, let's start with the first one. Let's start with this equation. Well, it's a second degree linear homogeneous ODE. We should write down the characteristic polynomial. M squared plus lambda squared is equal to 0. Therefore, M is equal to plus minus I lambda, right? Jeez. It would be C1 cosine of lambda x plus C2 sine of lambda x. Okay, and therefore we know f1 of 0 is equal to 0. If we let x to be 0, sine of 0 is 0. Therefore, we get C1 cosine of 0, which is equal to 1. Get C1. This should be 0 because the boundary value condition is CF1 of 0 is equal to 0. So if C1 is 0, we don't have this term here. That term vanishes, right? Okay, what was the other boundary value condition? The other boundary value condition was telling us derivative of f1 with respect to x at the point A is equal to 0. Now, this is the interesting condition. Before that, any question? Okay. Okay, so the other boundary value condition, which tells us derivative of f1 with respect to x at the point A should be equal to 0. Also, we know f1 was c1 times cosine, c1 was 0, plus c2 sine of lambda x. But let's compute this derivative of f1 with respect to x, right? What is derivative of f1 with respect to x? The derivative of f1 with respect to x is equal to lambda c2 cosine of lambda x. What is it at the point A? Derivative of f1 with respect to x at the point A is equal to lambda c2 cosine of lambda a. These should be equal to 0, right? There are a few different cases here. Well, either C2 is 0, but that's not interesting. If C2 is 0, C1 was also 0, so F1 would be 0. If F1 is 0, W is 0, we don't want that. So let's assume C2 is non-zero. If C2 is non-zero, we can divide everything by C2. We get lambda cosine lambda A equals 0, right? Now there are two cases. Either lambda is equal to 0 or cosine of lambda A is equal to 0. Now we should investigate both of these cases separately. They're both interesting. This thing is here case number 1. This thing here is case number 2. And we should consider each of them. We should see what is the result of each of these things, right? Okay, let's see. Which one should we try first? Well, let's first try to see what happens if lambda is equal to 0. Let's see. I don't want to spend much time on that, but let's just try that to see what we would get. So suppose lambda is equal to 0, right? What does that tell us? So our solution, f1 of x, was equal to c2, a constant, doesn't matter anymore, just a constant cosine of lambda x, sorry. Now we are saying let's lambda to be 0. So this would be equal to C2 cosine of 0. Therefore, it's a constant C2. So this implies f1 of x is equal to a constant C2, let's say. Okay, that is one answer. Let's consider the other equation. We have another equation for f2, right? What was the equation for f2? Derivative of f2 with respect to t was equal to this lambda squared, let's see, lambda squared times, oh, we can't have that. Sorry, I forgot. We can't even have that. Because if lambda is equal to 0, sorry. Because if lambda is equal to 0, remember, c was equal to minus lambda squared. If that's 0, it means c is 0. We already have showed that is not possible, right? So this case is not correct. That case doesn't appear. Sorry. That rules out. So lambda can't be equal to 0. So lambda can't be equal to 0. Great. That's very good, actually. Why? Because if lambda is not 0, the case number 1 can't happen. We can only have the case number 2. Cosine of lambda a must be equal to 0. If the function w, if it's possible to write it as f1 times f2, the only remaining case is cosine of lambda a is equal to 0. So the only remaining case, which should be true if our assumption is correct, is cosine of lambda a is equal to 0. Now we know if cosine of some angle theta is equal to 0, then theta is equal to, well, it's equal to k times pi for some k plus pi over 2, right? Cosine is equal to 0 at these angles, at these points, right? Okay. There is slightly better way also to write that down. We can say if if you are here it's like 2k pi. Being here, it's like 2k plus 1 pi, right? Or 2k minus 1 pi. So we can say it's 2k plus 1 pi plus or minus pi over 2. Anyway, so lambda a can be something like, say, pi over 2, 3 pi over 2, 5 pi over 2, etc. The minus ones do not appear. We don't need to consider them because we know cosine of minus theta is equal to cosine of theta. So considering the negative angles, that do not give us any new solution. So these are the things we should consider. So these angles. So in general, they're of the form, as you can see, 1, 3, 5. They're in general of the form 2k minus 1, an odd number times pi over 2. Okay, I should say minus pi over 2 here. So these two conventions are compatible. So if I divide everything by a, remember a is non-zero, so we can divide everything by a. You see lambda can be equal to an odd number times pi over 2a. These are values that lambda can get. There are infinitely many different values. So in order to differentiate between these different values possible for lambda, we show them with lambda with index k. So lambda k would be equal to 2k minus 1 pi over 2a. We can have each of them. All of them are possible values we can get in our solution. Okay, we have infinitely many of them. So k can be equal to 1, 2, 3, etc. up to infinity. Any question up to here? Very good. Well, so we know cosine of lambda a is equal to 0, right? That was our, so remember, what we learned was f1 is equal to c1 sine lambda x plus c2 cosine lambda x. One boundary value condition told us the first term is equal to 0. The other one told us cosine lambda x is equal to 0 at the point x equal to a, which is this condition. Now, if cosine of lambda a is equal to 0, well, lambda a has to be equal to one of these values, right? When cosine of something is 0, we know that angle is equal to an odd number times pi over 2, right? It should be something like pi over 2 or 3 pi over 2 or etc. So lambda a has to be equal to one of these numbers, one of the numbers of this form. This is their general form, 2k minus 1 pi over 2 for any natural number k. And then that gives me lambda is equal to 2k minus 1 pi over 2a. But it shows there are infinitely many different values for lambda. In order to distinguish them, I would say there's lambda 1, there's lambda 2, there's lambda 3, etc. Does that make sense? Okay, great. So lambda k is equal to 2k minus 1 pi over 2a. And f1 was equal to a constant times sine of lambda x. Its derivative was cosine, right? So f1 was c1 cosine plus c2 sine, where c1 was 0. So now we get a lot of different solutions because this lambda can be any of these numbers, lambda 1, lambda 2, lambda 3, all of them. Each of these things gives us one solution. So we would have f1. Let's show that with f1, 1. This is one solution, which is equal to a constant. I just don't write the constant. Sine of lambda 1 x, which is sine of pi over 2ax. There is another solution for f1. I would show that with f1, 2, which is sine of lambda 2x, which is sine of 3 pi over 2ax, and etc. We have f1 of k for any natural number k, which is sine of lambda kx, which is sine of 2k minus 1 times pi over 2ax. So we would have infinitely many solutions for f1. It doesn't just have one linearly independent solution. It has infinitely many linearly independent solutions. And they can be written in this form of trigonometric functions. Okay, so let's go back. We said, let's assume w is equal to f1 of x times f2 of t, and we try to find each of them. Now we have the solutions for this f1, and there is not just one solution. There are infinitely many different solutions. That's great. So we found solutions for f1. Now we should see if we can find any solution for f2. That's where we are now. Okay, what was the equation for f2? The equation was the derivative of f2 with respect to t over f2 is equal to this constant c, which we said let this c to be minus lambda squared for some number lambda. But now we know there are a lot of different values for lambda. So this lambda can be equal to, it can be equal to lambda 1 squared or lambda 2 squared or lambda k squared, where each lambda k is equal to 2k minus 1 pi over 2a. So there are a lot of different values. So we knew this thing should be equal to a constant, but now should be equal to a negative constant. But now there are a lot of, actually they have negative sign. But now there are a lot of different negative constants that it can be equal to. So it can't be equal to, first of all, it can't be equal to any negative constant. If it wants to have, if we want to have a solution for our equation, the one we started with, it should be equal to exactly one of these specific negative constants. Let's see if we can find a solution. So for each k, we can write down this equation. Partial derivative of f2 with respect to t. Actually, it's not partial derivative because f2 is just a function of t. It is ODE. Is equal to minus, say, lambda k squared f2 of t for any k. Therefore, derivative of f2 with respect to t plus lambda k squared f2 with respect to t is equal to 0. Well, we didn't need actually to take this to the other side. Maybe it was better if I haven't done that. I want to separate the variables. So let me erase this one. This wasn't the best way to do it. And again, because it's ODE, and I'm sure you're used to that notation more, let's show this one with f2, and I would just erase this one because it would be easier for you to really understand it's the same thing as we were doing before. So we do the separation of variables. So d of f2 over f2 is equal to minus lambda k squared times dt. Now we integrate both sides. Integral of df2 over f2 is equal to minus lambda k squared. It's a constant. Integral of dt. Now the left-hand side is ln of absolute value of f2 of t plus a constant minus equal minus lambda k squared t plus a constant. Let's show the constant with e. There should be a k. Well, no, this k is index. It's because we had different values for lambda. I'm saying that for any k. Oh, you mean 1 over k, the thing? Oh, I see. That's what you mean. I guess I chose the very bad notation, right? We had a constant k here, which doesn't really matter. I understand what you are referring to now. Let's show this letter with L. I understand it now. I'm sorry. We don't have L anywhere, do we? Okay, I don't erase the previous case so you would understand that we have two different letters here. One is L, one is K. So let's not confuse them. So I think someone else also asked this question. Maybe that was the source of confusion. Here, K is just the integer, the natural number appearing here, which I should have used L. And there is another K here. That is, you're perfectly right. So there should be just one K here, one K here, one K here, and one K here. So let me write down, so let me correct this page so it wouldn't confuse you. So here we would have lambda L. Yeah, because we have really we need a lot of letters. We don't have enough letters really. So here we would have minus k lambda L squared minus lambda L squared. And then there was minus k lambda L, then minus k lambda L, plus this constant. This is the constant of integral. Okay, fast. So if I raise both sides, if I take exponent from both sides, the left-hand side would be the absolute value of f2. The right-hand side would be e to that thing times a constant. We would get absolute value of f2 is equal to a constant. I don't know what let's just write constant. I think we've used every possible letter. E to the minus lambda L squared k t. So f2 would be plus minus that constant. So because I'm looking for the linearly independent solutions, at this point, I don't care about the constant. So take the constant to be 1 or minus 1, something which cancels the plus minus coming from absolute value. So take f2 to be e to the minus lambda L squared k t. So great, for each L, we have one f1 L, and now we have one f2 also L, because for each L, we have one of these solutions, right? It's not just, there's just one solution. There are infinitely many f1, there are infinitely many f2. So if we multiply these two things, we get W, but there are infinitely many different solutions for W. So I would show that with W of L, X, and T to be F1 L, F2 L. And the general solution should be a linear combination of all these things. So it should be a linear combination. This L should go from 1 to infinity. We should have a constant. We use BL because of relations to Fourier series. F1L was sine of lambda LX. Lambda L was 2L minus 1 pi over 2AX. F2L is e to the minus lambda L squared, this thing squared k t. So this is the general form of the solution to this equation. There is still one thing or more than one, infinitely many things. The things which we still don't know what are their values are these bn's. These are still unknown. So we have already used our boundary value conditions. In order to find these things, we should use the initial condition. Okay, let's have a break. Let's have a few minutes break and we would continue from here. Okay, let's continue. So we got to this point that we found what is the general form of this function W, which is the solution to our equation. The only thing which we don't know, well, there's not just one of them, there's a sequence of them, are these constants BL. We need to find these constant BL. And we should use the initial condition to do that, okay? Okay, so let's rewrite the things we know. Now we know W of X and T is equal to the sum. L goes from 1 to infinity. BL, sine of lambda L, lambda L X e to the minus lambda L squared KT. There is something that we should remember. If this is W, if we add V to that, so if I just add V to that, it should be equal to U. But V was equal to a constant T naught. So if I add constant T naught, this would be the answer to the equation, right? How can I find this constant B? How can I find this BL? So if I find this BL, I would have the solution to the original equation, right? Okay. Okay, so remember the initial condition tells us that W at any point X at the time 0 is equal to Fx minus Vx, which here is just T naught. Okay. Well, what can we do with this thing? So let's T to be equal to 0. This is what we have here. We would get sigma L goes from 1 to infinity BL sine of lambda L x e to the 0, which is 1, is equal to Fx minus T naught. And these are the things we are looking for. This is very similar to what we did to find the coefficient of Fourier series, if you remember, right? So if I want to find B, for example, M, any of these things, I can multiply both sides of this equation by sine of lambda mx. So multiply both sides. Multiply the equation by, say, sine of lambda mx, where m is just any natural number. Here L changes, goes from 1 to infinity. M is a constant, but it can be any of them. So we would get the sum. L goes from 1 to infinity. BL sine of lambda Lx sine of lambda mx. It is equal to sine of lambda mx times fx minus t naught. Now integrate. Integrate both sides of the equation with respect to with respect to x, the variable x. So the integral of the right side would be integral to the derivative of the left side. Okay. And let's take derivative from 0 to a. From 0 to a. You remember, under some assumptions, assumptions on convergence, which here I'm going to assume, we can interchange the places of the sum and integral. So I would erase the integral from outside and I would move it to the inside of this sum. And this BL is a constant, so BL also comes out of the integral. So it would be like that. Now we have computed these sorts of integral before. This is very similar to something we've done before. This integral would be 0. This integral is 0 unless L is equal to M. So if L is not equal to M, this integral is equal to 0. So all the terms there, all of them, their integrals are equal to 0, but just one of them. And that is the one where L and M are equal. Okay, so let's go to the next. That one term, which the integral is not equal to 0, that one, the integral would be equal to, let's see, the integral would be equal to a over 2. So on one side, we have a lot of terms equal to 0 plus bm, this is where m and l are equal, times a over 2, that would be the left-hand side. The right-hand side would be, what was it? It was the integral of 0 to a of sine of lambda mx times fx minus t naught dx. That was the right-hand side. So we were looking for all these numbers bm. So for any m in the set of natural numbers, bm is equal to 2 over a, integral from 0 to a, sine of lambda mx fx minus t naught dx. Now we have the solution to our equation. So we know what are the values of bm. Then u would be equal to t naught plus sigma bm. Let's show it with m, goes from 1 to infinity, where bm is this thing up here, sine of lambda mx, which we know what is lambda m, e to the minus lambda m squared k t. This is the solution to the equation. Here we have it. Is there any question about this problem? Okay. So if not, we can continue. Today I'm going to jump from the section 2.6. It's just another example, 2.6 of the book. I'm not going to go over that. It's a slightly different, just boundary condition. If we have time, we would go over that next week. But here now I want to finish the material for the exam. So let's start talking about section 2.7 of the book. Okay, so let's start the section 2.7. So here we have what is known as the Sturm-Liouville. Well, I'm not sure if I can write down Leoville correctly. Leoville problems. Okay, great. So it is very similar to the equation we just saw earlier. So we had, say, we had some f1 of x, and we had some f2 of t, right? Let's focus on the f1 part. The equation we had for f1 was of this sort. We had f1, the second derivative of f1 of x with respect to x, over f1, it was equal to minus lambda squared. And lambda could have it could have a lot of different values. It could be lambda 1, lambda 2, etc. So we could, because it's just function of one variable, I would use dt f1 d squared f1 dx squared with respect to x plus lambda 1 plus lambda squared f1 of x equals 0. So this is the equation we had earlier, right? We had different types of, so this is the equation, but we also had boundary value conditions. The boundary value condition sometimes was of this sort, f1 at 0 is equal to 0, right? Sometimes it was, let's say, equals a constant. Sometimes it was derivative of f1 with respect to x at some constant a is equal to another constant. This was the sort of the questions we had. Now we can generalize this question. So rather than having a condition for f1 or derivative of f1, we can have a kind of mixed condition, okay? So the sort of condition we can have, so the same equation, but with mixed boundary value condition. So we had two conditions. Here we also need two conditions, okay? So the condition would be something like this. F1 at 0 times a constant, say alpha 1, plus derivative of F1 with respect to x at a times another constant, say minus alpha 2. That's just for convention, actually, equals 0. And we should have another condition. Let's write both of them at 0. Sorry. Let's say both of them are written at 0. That's one condition. The other condition would be a condition for the value of F1 at the other boundary. F1 at A, so we have this rod. There is x equals 0 here. There is x equal A on the other side. And the derivative of F1 with respect to x at A. Let's say we have a condition for these. So let's say a linear combination of them is equal to 0. Okay, something of that sort. That is some sort of boundary value property we can find. Okay. Okay. So the point is that, as we saw, for any lambda L, we could get one of these things, right? So we had a lot of different lambda. So for example, let's say we have lambda n and lambda m, two different values for lambda. For each of them, we got one F1. So let's show one of them with F1n. Let's show the other one with F1m, right? So each of them satisfy this condition. So F1n would satisfy this condition. With lambda n here squared, F1 of n of x equals 0. And F1 of m would satisfy the same condition, but that constant lambda is different here. Okay, so we have these two equations. Okay, now let's consider these two equations at the same time. Let's think about them as a system of equations. Let's, rather than solving them one by one, let's try to look at them at the same time. Let's see what we would understand. Now, multiply the first equation by F1m, multiply the first equation by F1m, and multiply the second equation with F1n. Okay, with the other variables. So this one is for n, multiply that with F1m. This one is for m, multiply that with F1n. Let's see what we would get. So we would see the second derivative of F1n with respect to x times F1m plus lambda n squared F1n times F1m is equal to 0. That would be the first equation. The second equation, well, we should change the place of m and n. It would be the second derivative of F1m times F1n plus lambda m squared F1m F1n is equal to 0, right? Now, if we subtract, well, we can take F1, we can take these two terms to the other side. Let's take this term to the right-hand side, okay? To the right-hand side equation. So it simply becomes negative. So it would be equal to negative of that if I take this term to the right-hand side of the equation. I can do the same thing with the second equation too. That's what we are going to get. We would have two equations. The right-hand sides are almost equal. And, okay. So now let's let's multiply one of them with -1. Let's multiply, for example, the second equation by -1, and let's add these two equations. Let's add them. So the result would be the second derivative of f1n dx squared f1m minus the second derivative of f1m dx squared f1n. This would be the left-hand side. The right-hand side would be lambda m squared minus lambda n squared is times f1n f1m. This would be the equation we would get. Okay. Now here we are assuming lambda m and lambda n are different. N and m are different, therefore lambda m and lambda n are different. Okay, so this thing is here is non-zero. Okay. Now let's integrate both sides. Let's look at the right-hand side. Let's look at f1n and f1m. Let's look at this thing. If we take integral of this thing from 0 to a with respect to x, what would be the value of this integral? Let's look at the previous example. In the previous example, this was sine of 2, say, n minus 1 pi over a. The other one was sine of 2m minus 1 pi over a. So this integral from 0 to 1 is equal to 0. So this integral is equal to 0. We have, remember, we had a section on these integrals. We call them orthogonality, I think. So these integrals are equal to 0 when n is not equal to m. Okay. Knowing that, if we come back here and if we integrate both sides from 0 to a with respect to x, this part is constant. Well, not being non-zero doesn't really matter, actually. It's just constant. What matters is that this part, this thing is constant. It comes out of integral, right? So I can move integral inside. So I can move the integral here. And this integral inside is equal to 0, as we have seen before. So the right-hand side is equal to 0. Therefore, the left-hand side has to be equal to 0. Okay? The integral of the left-hand side should be equal to 0. Let's write that down. So the theorem we have, integral from 0 to a, the second derivative of f1n dx squared f1m minus second derivative of f1m dx squared f1n. This integral dx is equal to 0. Okay. Now, we can also think about this integral in a slightly different way. Let's forget for a second that this integral is equal to 0. Let's look at this integral again, and let's try to compute that. How? Let's try to do integration by parts. So let's apply integration by parts. Let's look at each part. So we have two integrals. Let's break it into two integrals. One is integral of df1, d squared f1 dx squared f1n f1m from 0 to a. The other one is minus integral 0 to a df1 m second derivative with respect to x from f1 and dx. Let's compute these two using integration by part. How? Let's look at one of them. The other one is similar. Let's look at this one, for example. Okay. So we should choose what is u. We should choose what is dv. So let's say u is equal to f1m, and say dv is the second derivative of f1 with respect to x, f1n with respect to x. Okay, if that's the case, du would be derivative of f1m with respect to x dx. And if we have the second case, v would be equal to, well, we just in some sense cancel one derivative. Actually, there is dx here too. So v would be equal to first derivative of f1n with respect to x. Okay, so if we apply integration by parts, so applying integration by parts, we can see integral from 0 to a d squared f1n dx squared f1 m dx is equal to, this is u dv, it's equal to uv minus integral v du, right? So it would be integral to uv. What is uv? U was equal to f1m. What was v? It was the first derivative of f1n dx minus integral of v, which is df1 n dx, du, which is df1 m dx 0 to a. We have the same thing for the other integral. So if we write both of them and if we subtract them, the thing we are going to get is this one. So we would see integral from 0 to a of, okay, I would just write it down. This from 0 to a minus the other integral, v du. Minus the other term. Minus the other term, but the other term is the same actually, I think, right? Yeah. Okay, as you can see, these two terms are the same, right? So their subtraction would be 0. So this integral is equal to 0. Okay, right? Now, on the other hand, this other integral, let's go back. Let's see what we had before. The theorem was this other integral is also equal to 0. So come back here. This other integral is also equal to 0. Therefore, what we have here should be equal to 0, right? It must be equal to 0. Let's write that down. So df1 n dx f1m minus df1m dx F1n. If we evaluate this at A, minus if you evaluate it at 0 should be equal to 0. This is another equation we would get. Okay. Now, have this in mind. Remember, we had also some boundary conditions, boundary value conditions. We have 15 minutes. I should try to be a little faster to get to the bottom of this discussion. We had two boundary value discussions. Remember, what was them? One of them was alpha 1, the general form, f1 at 0 minus alpha 2 derivative of f1 with respect to x at 0 is equal to 0. That was one of them. The other one, this is one of them, the other one was beta 1 f1 at a plus, it's just convention to use minus, it really doesn't matter, because they're constant, it's minus would be another constant. Beta 2 derivative of f2 with respect to x at a would be equal to 0. Okay, let's look at one of, well, we can look at one or two of these assumptions. Let's focus on one of them. Let's look at the second one. This is supposed to be correct for each f1 which satisfies this equation. Therefore, it should be correct for, it should hold for both f1n and also f1m. It should hold for both of them, right? So let's just write that. So beta 1 f1 n of a plus beta 2 partial f2 n partial x at a should be equal to 0. That's one. The same thing should hold for f1m. So I would just write down the same thing for f1m. Okay. Now, this thing can be written in a matrix multiplication form. You see, do you remember we had, for example, if we had ax plus by equals 0 and say cx plus dy equal to 0, we could write down this thing as a, b, c, d times xy equal to 0, right? I can write, this is completely similar. So here I have beta 1 times f1 at a plus beta 2, etc. Okay. So here I think about beta 1 as like x in this equation and beta 2 as y in this equation. So our constants a, b, c, d are these things. We can put these things in a matrix, just like this matrix here. Now, from basic linear algebra, we remember when we have a, b, c, d, x, y being equal to 0, if we want to have a non-trivial x, y, if we want there to be some x and y, which is both of them are not equal to 0, we should have some condition on this matrix A, B, C, D. Does anyone remember what was that condition? What is the condition on this matrix A, B, C, D, such that if that holds, we can find some x and y, which this solves this equation? No, that's unfortunately not true. So if I call this matrix A, and I can write down the equation like this. This has non-trivial solution if determinant of A is equal to 0. In other words, if AD minus BC is equal to 0. Going back to our equation, it means the determinant of the matrix formed by these elements here should be equal to 0. The elements here, this element one of them, the other one is this one, the other one is this one, and the other one is this one. The determinant of the matrix for by these things should be equal to 0. So it tells us that F1m dF1n dx minus F1n dF1m dx. This is the determinant at the point, well, at the point A. Everything is written at the point A. This should be equal to 0. This means that the determinant of the matrix we had there, that thing should be equal to 0. Okay. Now the same thing is correct. Same is correct at the point x equal to 0. So rather than A, we can have 0, and the same thing should hold. We have the same equation. These are called the orthogonality relations. So this shows that if we plug that into equation we started with, it shows the integral we started with. It shows F1n, F1m dx from 0 to A is equal to 0. So this is not correct only for the case which we computed, where F1n and F1m were sine of 2k minus 1n over A. It's correct in all similar cases. This is a specific example. Let me finish by just introducing these equations. This is a specific example of a more well-known problem, a more general problem known as the Sturm-Liouville problem. So the equation we had, remember, the equation we had was second derivative of f. I wouldn't write f1 anymore. We're just talking about one function here. With respect to x here, so suppose f is a function of x here, minus, or say plus, actually it was positive, lambda squared f equal 0. This was our function. This was our equation. Actually, I want to generalize this thing. So rather than derivative, the second derivative of f dx, the more generalized version is like this. Suppose s is a function of x, a given, specific given function. Multiply that by df dx. Take derivative of that with dx. Minus. Suppose q is another known given function, f of x. Plus lambda squared, suppose p is another given function, f of x is equal to 0. This is called the Sturm-Liouville equation. So we saw a general form of that. The form we saw, if we let this s of x to be equal constant 1, if we fix q of x to be constant 0, and p of x to be constant 1, we would get the equation that we solved, right? So because if s is 1, this would be 1. So we get d of this thing, which is the second derivative, is just what we had, right? We did not have this term. So if q is 0, this term would disappear. And we had lambda squared f. So if p is 1, that term just becomes lambda squared f. So this is what we solve, is a general case of a more general equation called Sturm-Liouville equation. The boundary value conditions we saw, they were conditions either on f of, say, 0, what is its value, or derivative of f with respect to x, either at 0 or at a. Now this Sturm-Liouville equation is kind of more general in the sense we just saw. It gives us a linear combination of these two things. So the equation is something of this form. So one boundary condition would be like that. So rather than being a condition for f of x or d of f of x, it's a condition under linear combination. Beta 1 of f of a plus beta 2 df dx at a equals 0. So this is the type of boundary value condition we have. There are some assumptions here in this Sturm-Liouville thing. S of x is differentiable. The function which appears here, of course, should be differentiable, at least, well, in this course, because we are taking derivative of that, right? So it should be differentiable. It might have weak derivatives, but it's given. So here we assume it's differentiable. And the derivative should be continuous, and s prime of x should be continuous, or at least piecewise continuous. Same thing for p and q. We want px and qx. We want these things also to be continuous. Another assumption here is that for us, s and p, they were both equal to 1. So another assumption is that both of these functions, s and p of x, we want them to be always positive, not 0, okay? So q can be 0, but s and p, they should be continuous, okay? And there is another assumption, and that's why here this minus makes sense. We want these numbers alpha 1, alpha 2, beta 1, and beta 2. We want all of them to be either positive or 0. We want them to be non-negative. So the alpha I and beta I, they are either positive or 0. Okay, non-negative. And another thing we want is that we don't want both alpha 1 and alpha 2 to be 0 at the same time. So at least one of them should be non-zero. Same thing holds for beta 1 and beta 2. We don't want them to both to be non-zero at the same time. Such equation with these boundary value properties are called Sturm-Liouville equation. Now, what we proved here, the theorem I just proved, was that if f, let's use another function. Say g1 and g2 are two solutions to this equation, two solutions to this equation, d dx, sf minus qf plus lambda squared pf equal to 0, which they satisfy also the boundary value conditions. They satisfy what we just proved. If we multiply them to each other, they are not the same solution. They're different solutions. Their integral from 0 to a dx would be equal to 0. This is called the orthogonality condition. So in another sense, we talked about solutions to an equation like vectors, right? We said two solutions are linearly independent. Usually we talk about vectors being linearly independent, right? So it seems we are thinking about solutions as vectors. They can be linearly independent. We can consider their linear combination and things like that. So this thing, sorry, there should be actually px here too. The correct form is that g1, g2, px, dx equals 0. In our example, px was 1. So this thing is actually, in some sense, you can think about it, define it as inner product of g1, g2. Okay, this is some sort of weighted inner product for functions. So in some sense, it says solutions, different solutions, which they correspond to different eigenvalues. So let's say this corresponds to gamma 1, this one lambda 1, this one corresponds to lambda 2 for this lambda here, just like our example. Different solutions are orthogonal. They are normal to each other. Just like when you have two vectors satisfying some linear equation with different eigenvalues. That's what you would expect. Okay, that's the assumption. Okay, we are done. So this is the end point where we are going to see in the exam, because it's just what we got to. So it's there's one page left from this section. We would talk about that, but we are not going to see that in the exam, because this is where we got, and I want you to have time to study. So if you are looking at recorded videos, then, well, this is the end. This is where you would see in the midterm. If you are looking at the lecture notes, everything in the lecture notes. If you are looking at the book, page 178, we studied theorem 1. So we finished the last thing you need to know for the midterm is theorem 1. Okay, next week I'm going to solve a few more problems. I'm going to go over section 2.6, which is just another example. I might review this section a little bit, because the first time you see this, it might be a little confusing. And then we would talk about the other theorem in this section. We would solve probably one more example. Okay, is there any question? Any question about the exam? Okay, if not, it's a good time to end today's class. Have a good weekend, everyone.